Hey Kyle, can you go to that website just to see how you're coming up?
Say something. I'm not going
Okay. Yeah, we might create feedback, so you probably want to listen live.
Yeah, I was just.
That's the best thing. Okay. Watch the stream.
Yeah, but
Yeah.
Are we going?
Yeah. Hey guys, so I'd like to welcome you all to our discussion on the Southeast Regional 2011 problem set. So Wendy has been kind enough to drop by and discuss the solutions to the problem. He's going to be going through the code for all those other solutions. And the code has been posted on this website, cc.cartaker.edu/skillwebtopras/SER 2011. So you can just look at the code while he's discussing the solution. Thanks, Wendy, for being here. By the way, Wendy is the Chief Judge for the Southeast region. So, Wendy.
Hi there. My full name is David Van Brackle, by the way, but Van B is what everybody calls me. And as Tapra said, I am the Chief Judge of the Southeast Regional Contest. Someday let me do a lecture with you on how we pick the problems, because that is quite a process we go through. It takes about 6 weeks for us to choose the problems, actually a little longer than that. We start off with a call for problems throughout the region, and we close the call for problems right around Labor Day. And then we spend about 3 weeks evaluating them, trying to determine how hard they are and how much we like them. We then spend a week of problem set selection to pick which problems we want to be in the set, which is based on how hard they are, what their difficulties are, and how much we like them, but also what styles of problems they are, what kind of mix we want. And then we spend a full 2 weeks on quality control, where we read through the problems, make sure that they're stated the way we want, make sure that the limits are what we want them to be. We create the test data in that period, make sure the test data works. And then we deliver the problem set a week before the contest, actually the Monday of the contest. So this year we had a pretty good year. There were some disappointments that I'll tell you about when I get to them, but overall the problem set looked like it was pretty clean. We had very few statements of ambiguity. The judge data was all in order. There was nothing wrong with the judge data, so we were pleased with that. So I'd like to take some, are there any questions about how we put together the problem set for a minute before I actually go into the problem set? Okay, I'll take that as a no. The first problem in the problem set was called Sunday Drive. The idea of Sunday Drive was you've got a highway with up to 10 lanes, and you've got straight segments and 90-degree turns. So you needed to figure out how to get from the beginning of the highway to the end with the minimum amount of distance. If you're in a curve, you're not allowed to change lanes. If you are on a straight section, you're allowed to change one lane for every 100 feet of the straight section. This was very difficult for us to express. We tried to express it as clearly as we could. We still had some questions about whether it was 100 feet this way or 100 feet, at the angle, but we did the best we could to be clear about that. This is a standard, old-fashioned dynamic programming problem. a lot of our teams tried a greedy solution. And a greedy solution simply doesn't work. You cannot make a decision when you hit a curve which lane to be in, because you might have to pre-position yourself for later turns. So it's a dynamic programming problem. You create an array, which I've got right here. Best, where bests of ij is the best you can do from the beginning to the end of segment I if you're in lane j. Okay? So that's what best of ij is. It's the best you can do from the beginning of the road to the end of section I in lane j. Okay? And so from there, it's just simply a matter of starting at 0 and going iteratively. Section 1, Section 2, Section 3, Section 4, and looking at all ways you can move from lane to lane. And we'll take a quick look at that code. And this is going to be difficult to see. So we'll start here. Length sub I is the length of the ith segment. So if you divide that by 100, that will tell you how many lanes you're allowed to cross in this section. And while it wasn't explicitly stated, most of our teams figured out that the minimum distance that you could change lanes was to use the entire segment to do it. You would have been allowed to like cross in 100 and then go straight, but it's pretty obvious. We draw a highway here. It's pretty obvious that distance A is shorter than distance B, which is the sum of these two. So most people were able to figure out that you just use the entire thing to change lanes. So we're looking for the lowest distance. Ooh, what happened there? Oh, I did this. So J is the lane you're in, K is a lane you're crossing to. This is the number of lanes you've crossed. If we have enough length to do that crossing, then figure that distance, and if that's better than the best you've seen so far, make that the best. And the curves are really simple because you cannot change lanes. It's just math. It's just figuring out the radius of the turn. So Sunday Drive, the biggest catch was that some teams thought it could be done with a greedy algorithm, but no, it requires this old-fashioned table-driven dynamic programming. Any questions about Sunday Drive? Sunday Drive was one of two problems. We had a question before the webcast began about why there weren't more geometry problems. Every year up until now, we've had at least one that was pure geometry. We couldn't do it this year, but Sunday Drive was one of the problems that picked up the slack a little bit and had a little bit of geometry. It had, the Pythagorean theorem in there, and it had, pi times the radius to get the circumference. So it had a little bit of geometry. The second problem in the set was called Hexagram. The problem was, and let's see if I can pull up a copy of the problem set here. Move this down. On. Let's go to 2011. That's where I want to be. Problem set. Should do it. All right. So you take one of these things, and you put a number at everywhere that two lines meet, so that along every line, the sum is the same. With any set of numbers, how many ways is there to do that? Now, ignoring rotations and reflections. So how many unique ways are there to do that if you ignore rotations and reflections? So, I'm sure that Topraj has taught you programming by the numbers, right? So, what's the order of this algorithm? There's really only one way to do it, and that's kind of brute force. So what's the order of that algorithm? Come on, you get n factorial. How big can you go with n factorial?
10, 11.
10 or 11 is about the limit. How many things are here? 12. That's one too big. So you have to find some creative pruning. Now, we actually bumped the time limit up a bit, so you didn't have to be too creative with your pruning. One thing that you can notice is that there is only 2 types of intersections. Maybe you can close the door. There are only 2 types of intersections, the points and the internodes. And so you can have an order 11 factorial algorithm by simply taking the first number, fix it at a corner, see what you get, then fix it at an intersection, see what you get. The code I'm going to show you is a little more clever than that. Most people's code ran in about 20 or 30 seconds. This one ran in, I think it was between 1 and 2 seconds. Let's see here. The trick is pruning. You want to be able to prune permutations that aren't going to lead you to a solution as quickly as you possibly can. So it's that creative pruning, other than just simply starting in the right place. And here's how this creative pruning works. There we go. It was a matter of creatively numbering the intersections. So in my permutation, spots 0 through 11, this is where 0 went. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay? Instead of the way you might do it, you might go like 0, 1, 2, 3, 4, 5, 6, 7. You might do it like that order. I did it in this order. As soon as I hit 4, like I call this with 0 to place 0. I call it with 1 to place 1. I call it with 2 to place 2. I call it with 3 to place 3. As soon as I call it with 4, I've got 0, 1, 2, 3 placed. I know what my target number is. I know what my sum has to be. Okay. As soon as I place 4 and 5, as soon as I'm looking for 6, I know what it has to be. I know what my target number is. So that lets me start pruning very, very early. On the sixth recursive call, placing the 6th thing in the permutation, I can say this isn't going to work and can prune at that point. And then after placing 7, once I'm looking at 8, I can prune. And then 9, 10, and 11, each one of those I can do pruning. So the trick there was, it's just a standard permutation algorithm, but the trick was the pruning to get it down to where the numbers are manageable. Any questions on hexagram?
How do you check for rotations?
Oh, if you do, that's a good question. If you do the trick where you place something at the start, at a point, or at an intersection, then you will have no problem with rotations, because rotations will just put that thing at a different point or that thing at a different intersection. If you fix it at one point and fix it at one intersection, you won't have problems with rotation. And you will have exactly one reflection of each. So the number that you get from the recursive calls is double the number you want. You simply have to take the number you get from counting up and divide it by 2 to account for the reflection. Good question. Good question. Anything else? Okay. The third problem, was that folding? I'm sorry, was that, third problem was flooring tiles, right? Okay. Flooring tiles. You're given a number n, and you want to know, you've got n little tiny square tiles. Okay. Actually, no. You want to be able to form n rectangles. How many little square tiles does it take to form exactly n rectangles? You can't form too many. You can't form too few. You have to form exactly n rectangles. Okay? Well, so basically what we're looking for is a number that has exactly n factors that are less than half that number. Or actually, n numbers that are less than or equal to the square root of that number. If you take a look at any particular rectangle, there is a statement that, those two are the same, considered the same. That's 2 times 10, that's 10 times 2. So these two are considered the same, so you want to focus in on the smaller. And so you want to count the number of, you want a number that has a number of factors n that are less than or equal to its square root. Okay? So, if there are n numbers that, suppose it's not a perfect square and that it doesn't have an integral square root. Try the door lock if someone wants in. Whoa. Nobody's going to be listening to me. Holy moly, what'd you do? Guy, get a pizza for everyone? That's a lot of pizza there.
16 pizzas, that's the normal.
That's amazing. Man.
Come to Georgia Tech.
I've been here.
So you guys
Telling people on the
one by
webcast.
one.
Oh
so
yes,
pizzas
the
and
people on the
debate.
webcast. Come to Georgia Tech. So, if a number has n factors that are smaller than its square root, then it also has to have n factors that are bigger than its square root, right? So there are two cases. Case number one is you want a number that has exactly 2n factors. The other case is that you want a perfect square with exactly 2n minus 1 factors. Does that make sense? So if it's not a perfect square, then, for every smaller factor, there's a bigger one. For every smaller factor, there's a bigger one. For every smaller factor, there's a bigger one. If you want n smaller factors, you need 2n factors overall. Now, perfect squares cause us a problem because x times x, I mean the square root times the square root, it is its own little factor. So if you want n that are there, if you want n that are smaller, then you need n minus 1 that are bigger because the square root pairs with itself. Make sense? So you either want 2n with a non-perfect square or 2n minus 1 with a perfect square. Okay? So, but how do we generate that? How do we generate a number that has exactly some number of factors? Okay. Well, let's break it down into primes and see what we can do with primes. Let's start with 2. How many factors does that have? Loud. 2. 1 and 2. How many factors does that have? Come on, give me some feedback. I'm going to sit here and stare at the board all day if you don't give me some feedback. Loud. 3. Thank you. How many factors does that have? 4. How many factors does that have?
5.
Anybody noticing a pattern? See a pattern here? Okay. So let's do this. How many factors does this have? 2 times 3. How many factors does that have? Let's see. 1, 2, 3, and 6. Yeah, so that has 4 factors. 2 times 2 times 3. How many factors does that have?
6.
2 times 2 times 2 times 3. How many factors does that have? 8. multiplying by 3 doubled our number of factors. So what about 2 times 2 times 3 times 3? You need to see a pattern? So we can break this down into primes. P to the I, P to the J, P to the K, and that marker is dying.
I'll get you.
Yeah. Try the green one and the blue one.
That looks pretty good.
Yes.
So we want to break it into primes like P to the I, P to the J, P to the K, and so on, where I minus 1, well actually I plus 1, J plus 1, K plus 1, and so on, is equal to that target that we're after. Okay? Does that make sense? Well, it's n plus n. It's our target. Yeah, it could be 2n, it could be 2n minus 1, but it's our target. Target. Okay, there we go. So, if we break it down like that, clearly we want, I, J, and K, we want the exponent of 2 to be the smallest, and the exponent of 3 to be the next smallest, and the exponent of 5 to be the next smallest, because we want the smallest number possible. So, and that's kind of the key to the code. Let's come over here. Those flooring tiles. So in this code, n is the target. Let's take a look at the... So n is the desired number of factors. P is the smallest prime we should be considering. And if we're looking for a perfect square, there's some things we can do to make things a little faster. Most is the most of a prime that we can use. In other words, if we've used 5 2s, we don't want to use 6 3s. Right? So that's another way to prove. And then we return the minimum as stated. So find the next highest prime. Find the factors of n. If n mod I equals 0, it's the factor. F is the other factor. F is the bigger of the two, as a matter of fact. If f minus 1 is within the realm we're willing to consider, and make sure that if we're not looking at either we're not looking for a square, or if we are looking for a square, that the f is even. Break the factors up, same number on each side. Then get the possibility. If it really is a possibility, get the minimum and multiply it in, and then recurse to the next. And recurse to the next prime. So that's it. There were a couple of things to... The problem that we had with this, the judges had with this, was the limits. A lot of the judges are Java people. We don't have as many people who are as well versed in C++. So it was our impression that big integers give Java programmers an advantage. So we wanted to stay away from big integers. We've heard that C++ has some big integer libraries, but they're not as standard. And if your team has practiced on one set of libraries and they find another set of libraries at regionals, then you're at a disadvantage, even though C++ has big integer stuff. So there are a couple things. Calendars is another one. Those are things that you won't see at Southeast regionals because we don't want to give an advantage to one language over another. There's another problem we'll talk about later where we had to do the opposite, where C++ programmers had an advantage over Java programmers. We actually had to make a change to the problem to accommodate that. We'll talk about that a little later. But we needed to keep things small in order to keep big integers from being an advantage. That's why the limit of the input was 75. And that still gives you some really big numbers, but we told you what the biggest was so that you could easily do pruning without having to resort to big integers. Any questions about flooring tiles? Okay.
In this problem, in the problem set, it is said that the answer will be fitting at 64 integer, right? But actually, in the program, when you are writing a program, you have to do some you should multiply two integers, which will cause it to exceed 64 integers.
Which is why you need to do this. Only multiply if the rest of this you can't see it, but only multiply if it won't overflow. You needed to do a little check. Make sure it wouldn't overflow. We knew that. We knew that anything above, I think it was 31, would give you overflow and intermediate results. But you can avoid overflow and intermediate results by just checking first, by doing a division. This is the biggest number possible. That's the biggest number possible. It's not maxent. It's the number stated in the problem, which I think was 10 to the 18th or something like that. So this is the biggest number possible. And if what you're going to do is multiply it by possibility. So if this thing is not less than biggest divided by possible, then multiplying it by possible goes to something that's bigger than the biggest we've said will happen, so you can avoid the overflow. That is exactly why we put that statement in the problem set. In order to be able to filter out overflow this way, so you wouldn't have to resort to big integers. All right. The next problem, this one, I got some interesting things to say about this one. Vive la Difference. Easiest problem in the set. It is the first time, I believe, in the history of Southeast region that every single team solved at least one problem. And this was it. It was the easiest problem in the set. But that doesn't mean it was the easiest problem for the judges. There's some very interesting things about that problem that I want to talk a little bit about. First of all, is there any need for me to talk about the code itself? Everybody in the region solved it, so I think you understand the problem pretty well. I don't think I need to talk about the problem itself. Let me bring up a presentation here. Put that away. Put that away. Put that away.
We make an announcement just in case.
By the way, the source files in this presentation is at this website, so if you guys want to download that for people watching online or here.
So this is a brief statement of the problem. Okay? Take any four integers, absolute value of the differences, keep doing that, it'll eventually converge. This one converges in 6 steps. 1, 2, 3, 4, 5, 6 steps. They're all the same. That's where it converges. Okay? Notice the statement that I've put in bold and italics. In fact, it can be shown that if all 4 integers are less than 2 to the n, then it will take no more than 3n steps to converge. Kind of cool, huh? We have to be able to prove this. We cannot use this problem. We really liked it. We really wanted to use this as our hello world, everyone can get this problem. We really liked it. But we can't unless we can prove that it converges quickly. Why not? Because good teams like you are going to think there's a trick. And they're going to start looking for mathematical ways to do shortcuts when all we really want is an iteration. And you're going to be, well, should we try one and get an incorrect judge run if we run out of, And we can't simply say, well, we'll just make the judge input so it'll converge quickly. We can't say that because in your test data you might generate random data and you will have no assurance that the test data that you generate converges quickly. So, in order to use this problem as our simplest problem, we have to be able to prove this. We have to be convinced of it. So let's talk a little bit. And this problem came to us from the other region we were sharing with, which was the Rocky Mountain region. The original problem stated it the other way. Given n, a number of steps converges, print out a, b, c, d, 4 integers that going through this process will converge in that number of steps. That was the original problem. And it had some absurdly small limits that we don't like absurdly small. I mean, 75 was the limit on this was like 54 or so. We would have put it at 50, and we didn't care for that. But we liked the reverse problem. But some things that came out, first, if k is an integer, then these four, this sequence, a plus k, b plus k, c plus k, d plus k, converges in exactly the same number of steps as a, b, c, d. So I can add a constant to every one, and it will converge in exactly the same number of steps. The proof is pretty easy. The k's cancel out. Yep, k minus k, k minus k, k minus k, k minus k. So in one step, you're to what it would have been with one step with without the k's in it. So any questions there? That's pretty straightforward, actually. We're good with that? Be more, yeah, we're good with that. Good. Thank you. Thank you. Another helpful fact: if k is an integer, then the same thing holds with multiplication. If a times k, b times k, c times k, d times k converges in exactly the same number of steps as a, b, c, d. And once again, we'll just throw it in there, and the k's factor out. And so, however many steps it took the first one to get down to 4 numbers that were all the same, it'll take this one the same number of steps. It's just that those 4 numbers will be multiplied by k. The k just factors on out. Okay? Good? And a corollary is that you can divide as long as these guys are integral. And there was a corollary on the previous one that you could subtract, but that's kind of obvious because I didn't say whether k was positive or negative. So, are we good with all that? Come on, give me them. There you go. All right, okay. Some more helpful facts. Rotations all converge in the same number of steps. That should be fairly obvious. I didn't show any proof, but it's just that you rotate it, and then the next one down will have the same rotation, and the next one down will have the same rotation. If they're all the same, then rotation doesn't matter. So any rotation will converge in the same number of steps. Cool? And also, let's talk about even and odd numbers. Let's let E be an even and D be an odd. I use D instead of O to not confuse it with 0, which is even. So, if you take an even minus an even absolute value, that's even, right? Even minus odd absolute value is odd. Odd minus even absolute value is odd. Odd minus odd absolute value is even. We all accept that. Everyone. Everyone in the room accepts that. Web people, you accept that. Can they talk to me? Can they?
No, they might be, but I don't know.
They're probably swearing at me by now. Are there people watching? Yeah. Can you tell?
15 current.
Pardon?
15 people.
Wow.
15,000.
It's going to be on YouTube, isn't it? Go viral. So, if A, B, C, and D are all non-negative integers less than 2 to the n, then that sequence of 4, through this process, converges in 3n or fewer steps. Okay? That's what we got to prove. We're going to prove it by induction. So, base case, n equals 1. 2 to the n equals 2. So if all 4 elements are less than 2, and they're non-negative, then 0 and 1 are my only possibilities. Right? People at home? Right? So, let's take a look at, if we have 4 ones, well, that's already converged. They're all the same, right? Right? Everybody say right.
Right.
All right, okay. 3 ones. Well, because of rotations, there are actually 4 possibilities with a 0 here, a 0 here, a 0 here, and a 0 here. But because all rotations converge in the same number of steps, I only really have to look, they're all just rotations of each other. I only need to look at one of those, right? So if we do this, 1 minus 1 is 0, 1 minus 1 is 0, 1 minus 0 is 1, 1 minus 0 is 1, I get to that. Okay. The next step, 0 minus 0 is 0, 1 and 0 gives me 1, 1 and 1 gives me 0, 1 and 0 gives me 1. And the next step, 1, 1, 1, 1. So it converges in 3 steps. Cool? Cool? Cool. 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 So 2's. Well, it's either this or this. And all other, I'll leave it as an exercise, a mental exercise to you to convince yourself that all other possibilities with 2 1s and 2 0s are rotations of one of those. Okay? So if they're all just rotations of one of those, then those are the only 2 I need to consider. There are intermediates here, and so either way, it takes less than 3 to converge. It either takes, in this case, it takes 2 steps to converge. In this case, it takes 1 step to converge. Either way, it converges in less than 3 steps. Okay? All right, so if there's only 1 1, once again, there are 4 of those possibilities, but I only need to look at one of them because all rotations converge in the same number of steps. So 1 1 0 gives me 1 0 0 1, 1 0 0 1. That gives me 1 0 1 0, and that gives me 1 1 1 1. So it converges in 3 steps. With our 0 1s, it's already converged. So, if n is 1, if all the numbers are less than 2 to the first, if all the numbers are non-negative and less than 2, it converges in no more than 3 steps. Are we cool? Cool. Cool. Next, assume it's true for n minus 1. Assume that all these guys are less than 2 to the n. Okay? So, let's take a look at these possibilities. First possibility is that they are all even. Okay? Suppose I've got 4 even numbers there. Okay? Well, it converges in the same number of steps as e over 2, e over 2, e over 2, e over 2. Remember that second helpful fact that you can divide by a constant? They're all even, so dividing by 2 keeps me in integers. And what can I say about these things? How big are they? Catch you by surprise. How big are these?
Half the size.
Half the size. How big were the original numbers? Less than 2 to the n. So these guys?
Are also less than 2.
Less than 2 to the n minus 1. So, my base case. That's my induction. So this takes the same number of steps as that, which is cool. So let's consider all odd. If they're all odd, well, then all I have to do is take d minus 1, d minus 1, d minus 1, d minus 1, and what do I get? All even. And that converges in the same number of steps as something where all the numbers are less than 2 to the n minus 1. Swimming so far. What if I have 3 even numbers? Well, an even gives me even. Even gives me even. Even odd gives me odd. Even odd gives me odd. That gets me to here. That gets me to here. That gets me to here. So it takes me 3 steps to get to something that converges in less than 3 times n minus 1, which is my assumption, my induction. Good? With 2 e's, it's either that or that, and once again, just like in the 1 0 case. With 1 e, it's just like the 1 0 case, except it spells the word d, which is kind of funny. But other than that, it converges in 3 steps. So, it takes a maximum of 3 steps. No matter what these numbers are, no matter what they are, if they're all less than 2 to the n, it takes a maximum of 3 steps to reduce them to something that converges as fast as something with all their numbers less than 2 to the n minus 1. So it takes 3 steps to converge to something that takes 3 times n minus 1 steps, and that, do a little bit of algebra, gives us our... And there it is. 32-bit integers converges in less than 100 steps, no matter what they are. Before, and once again, this is so we had to prove this. We couldn't. This was not something that was known. This was not something that we could look up in a book. And it took a while to prove this. When we were first looking at it, we were looking at like going from n to n plus 1 instead of n to 2 to the n, or 2 to the n to 2 to the n plus 1. And I wrote a program on a machine at work and ran it for a couple of days, generating random cases and seeing what the largest numbers were. It generated 700 billion cases, and the largest N we got was 23. 23. So these things are few and far between. And it converges really, most of the cases in the judge data, if you've taken a look at it, converge in like 4 or 5 steps. No matter how big the numbers are, it converges in like 4 or 5 steps. It's amazing. So, here's something that I'm going to leave as an exercise. Now, pretend you're a judge, and you have to create judge data for this thing. You don't want a bunch of cases that all converge in 4 and 5. You want to get up into the 40, 45, 50 range. Which means you have to solve the original problem. Which means you have to take an N of 50 and find 4 integers that will take 50 steps to converge. So I will leave that as an exercise to you to have fun with, to try to figure out how the judges could create that kind of judgment. Oh, wasn't that fun? And now, this was the easiest problem in the set. This is what the judges had to go through for the easiest problem in the set. To make sure that it was the easiest problem in the set. Any questions? Everything good? Enjoying the pizza? Are we?
Do you want some pizza?
No. Not while I'm talking. That would be bad. So what came after this? I think it was robot?
Yes.
I think robot is the next problem. So let's see if I can find it here. Robot. It is.
All the problems you've done ever?
Pardon?
Regional? Is that all the problems you've done for regionals on the side?
That is all the problems that we considered this year. We had a total of 30 problems that were under consideration this year, and I wrote a solution for probably 20 to 25 of them, just to make sure that I understood the problem, make sure I understood the ins and outs of it. So yeah, that's just this year. I told you, it is a very intense process, the process of putting together the problem set. It is not, a bunch of people getting together in a smoke-filled room 24 hours before the contest saying, I think this would be kind of a cool problem. No. There's a lot of work that your problem selection committee does in order to produce a clean problem set that is worthwhile, that covers all the bases we want it to cover, that covers the range of difficulties and problem styles that we want to cover to make sure that the data is clean. It is a lot of work. All right, so let's talk about robot navigation. This would be a really simple breadth-first search, except for 2 things. First, the forward X business. Instead of just going 1, you could go forward 1 or 2 or 3 or 4 or 5. That adds a little complication, but the biggest complication comes about because you need to count the number of ways of getting to the target point with the minimum number of instructions. Right? And like many problems that you will see in Southeast Regionals, and like many you saw here, you cannot do it one by one. If you try to do it one by one, you probably got runtime limit exceeded. Our biggest case, I turned on big integers just to see what I would get, and the number that I got for the number of paths was, it was over a Google. It had more than 100 digits. So you can't count that. You can't count that one by one. So the trick is, as you're going, to keep track of how many ways can I get to this node. If I can get from this node to that node, well, then I've got that many ways of getting over here to that node. So you need to keep track of not only the length of a path to the given node, but also the number of programs the number of shortest programs that you have found that will get you to that path, or get you to that target node. That is the essence of the algorithm. It is simply a breadth-first search, but with that additional little trick of having to keep track of the number of ways of getting it. So if we look at the code here, and that's also why the mod of 1,000,000. You need to, the numbers get big. So here we go. Paths is a count of the number of ways to get to this particular. Now these are 3 indices. Okay, why 3 indices? What do the 3 indices represent? This is a place on the grid. Why 3 indices? Say that again? Ding, ding. Give that man a piece of pizza. Yes, exactly. So, we need to know, because it takes a full move to stay where we are and turn. So, a state is more than just a position on the grid. It's a position on the grid and the direction you're facing. So the 3 indices of this are x, y, and d, the direction you're facing. Okay? So we need to count the number of paths modulo 100, or modulo 1 million. You need to count the number of paths to get to a particular state. And you also need to remember the length of the shortest path that got you to that state. Make sense? So make move here, I'll talk a little bit about make move. So this is to go to I, J, direction D from a given state. If we haven't been here before, then it took us one more step from the previous state to get here. That's the length. And this is a new state we haven't seen before, so we're going to put it on the cube with that additional length. Oh, man. It's so annoying. Got to go all the way back. Here we go. So if we've previously gotten here with a path at equal length, or if we got here with a path equal in length before, then all the paths that got you here, that got you up to the previous state, got you here too. So add them into your count and mod for large numbers. Make sense? That's it. That's really all there is. This is just to show you some other Judge Insight stuff. There's some stuff the judges have to do that you don't have to do. Keep account of the number of X's and the number of starting points. And if that's ever not one, if there's ever more than one or less than one target, more than one or less than one starting point, then let us know that a particular case is malformed. So this is part of the way we keep your data clean. And from there, it's just a breadth-first search. There's some trickiness here. Found path is the length of the path we found. If the length of this path is longer than the shortest path we found to the target, then we can break. If we've reached the target, remember the length of that path, but we can't exit. Most breadth-first searches, once you reach the target, you exit. We can't exit here because there might be other equivalent paths that we have to find and count, right? So if we've reached the target, remember the found path, but we don't break. Don't break yet. And we can just take a look at turning. God, this is annoying. Turn right. Turn left, move forward, that's it. Turn right, just take the direction, plus 3 mod 4. Turn left, well, that's left. Right is plus 1 mod 4. Move forward, come up with a new J, a divide, a new J, and keep going while you're on the board, and you can't see it out here, but it also checks for a grade. That's it. Any questions about robot navigation? All right. I think folding game was next. Is that right? Folding game. Folding game was not, how shall I describe it? It was not, did not require a difficult algorithm, but it did require a lot of thinking through. And there was one particular thing that I know caught me, and I believe that it caught a couple of a couple of teams too. what happens? Does someone have a piece of paper I could borrow or have because I'm going to destroy it?
Yeah, sure.
So we can fold like this, you know, and we can keep track of, you know, here's our origin. We fold like this. We can see where we touched it to see whether. But what if we fold like this? What if the K, what if that amount that we're folding is greater than half the height of the paper? Our origin changes. See that?
That got our first team too. That's why they were fixing it for a while.
Yeah, that caught me, as a matter of fact, while I was writing a solution to this problem. Other than that, I don't think I'm even going to show you the code. Well, I might, but the code will be posted this weekend. I'll get some code out there on serjudging.vanb.org. You know, all know about that site, right? serjudging.vanb.org. The trick was to fold it, read in the folds, fold it up, and remember it, and then see where the XY was, and then recursively unfold it. And if the finger was on a place like this, then when you unfold it, you figure out where these two spots are, and you call the routine recursively at each one of them, so you count the number of pages one by one. The number of folds was 20. So what is the maximum number of layers of paper? 2 to the 20. If we're doing programming by the numbers, about 1 million. Well computable. So you didn't need any tricks to try to break it down and try to count a whole bunch of folds at one time. You could just, you know, figure out where the point was on the paper. You know, unfold it, call recursively on those two spots. And if you reach the fold 0, add 1 to the total. Oh, this next one causes me great grief. Burnout. How many of you suffered from burnout?
Burnout by burnout?
I mean that in every sense of the word. How many of you this problem caused to suffer? This is, well, burnout. The frustration I had as a judge is that many teams, for some reason, thought this was an easy problem. And that's a frustration for me. This problem was a quicksand bog. It had all sorts of little tiny tricks and things that you could get caught up in. For advanced teams, that's fine. Teams that have aspirations of going to World Finals have to be able to work through problems like this. I have no problem giving a problem like that and making advanced teams fight their way through it. Beginning teams, less advanced teams, that causes me some grief. I'm going to have to figure out a way, yeah, the guy's playing a tiny little violin here. We're going to have to find a way as judges to do a better job of making it clear, you know, that this problem is not for the beginning team. This problem had 86 submissions, 0 of which were correct. Which, as a judge, is extremely frustrating. There were other better problems that some of the less advanced teams, particularly vampire numbers we had seen as the second hardest problem after Vive la Difference, the one that other teams should have gone to. But if you look through the scoreboard, you'll see lots of teams that have a correct judge of difference, a lot of incorrect judges of burnout, nothing else. And that, as a judge, is very frustrating. That we did not make it clear enough that this was an extremely challenging problem. The one thing, once again, programming by the numbers. Someone who has the problem set open. What was the biggest number? What was the biggest amount of time that n could be?
1 billion?
It was bigger than 1 billion? Was it? Or was it? I thought it was like 10 billion. Anyway, it's big. It's too big to go one by one. You cannot simulate this. You cannot go through and simulate it. Suppose you had a case like this, and there was a case like this in the input. A max case. And how many zeros do I need here? How many over zeros there? Is that a billion? It's a billion, isn't it?
Yeah. Sorry, I didn't have the problem set open. I just did it by memory.
So, on for 1, off for 1,000. Actually, I think this is like a million. I think a million was the top limit here. I don't remember, but it was whatever the max. Maybe it was 1,000. We'll use 1,000. That's good enough.
The K is 100. The M is a million.
M is a million. Okay. There was a case like this in the input. So, on for 1, off for a million. On for 1, off for a million. On for 1, off for a million. For a billion ons. You cannot simulate this. You have to take every grouping, compute the amount of time on and off for that grouping, and then somehow intelligently use that to say, okay, this grouping is this many, I use this many of it, you know. Another trick is, when you come into a grouping, is the light on or off. And that can be challenging because it flips under 2 conditions. I mean, both conditions have to be true. If the number of elements in the list is odd, and if the repeat number is odd. If either of those are even, then the light on, off, the light stays on or stays off. It stays in its previous state. It does not flip states. So both of those have to be odd. So, and also, there were some issues with the parsing. I'll have to go through and take a look at the judge data, but I don't think I had a single wrong answer on this problem. I think that every incorrect judge run was either runtime limit exceeded or runtime error. I might have gotten, maybe I'm wrong, I have to go back and check, but I remember those vividly. There were parsing errors, and the parsing errors largely were caused by this case, which I didn't think this was a special case, but evidently people got caught by it. That just shows how little we judges know. Something like this. A repeat within a repeat within a repeat. Is everyone familiar enough with the problem? Should I have given a basic introduction to the problem first? Is everyone familiar enough with the problem? Well, the idea was you had a pattern like this that describes a way of repeating numbers. And you've got a light bulb which starts on, and every time it hits a new number that's not a repeat, it flips states. Turns off, turns on, turns off, turns on. What's the amount of time until it's been on for its specified life? That's the problem. And this says, take a 6, repeat that 18 times, take that whole thing, repeat it 19 times, take that whole thing, repeat it 4 times. People thought there would be a space here. So I got lots and lots of parsing errors that this was not parsable as an integer, because they were breaking it up by space, and they were expecting a space to be here. But the problem says quite clearly that the spaces are only used to separate elements. And in particular, this is in the problem set, in particular, there will never be a space before a closed paren or after an open paren. Very explicit in the problem set. But there's still a lot of things. In fact, to Praj, I looked at your A teams, and they got a runtime error right about the first time one of those appeared in the judge set. So I think your A team made that mistake, or didn't parse it correctly. So, but it's, oh, okay. But you caught it. You did see that there was a mistake.
Yeah, because I rewrite the program again after
wrote that thing again?
Yeah.
You are a glutton for punishment.
He solved it later.
Jeez. I didn't want to solve it the first time. That thing's a mess. I mean, it's not algorithmically detailed, but it's not algorithmically difficult. But there are so many fiddly details that you need to keep track of that it is just it's a monster problem. We considered it a CD rather than an EF. What I mean by that, we considered it a problem that was among the harder problems at regionals, but still not hard enough to go to World Finals. Algorithmically, it's not. It's just a lot of care that you have to take for special cases. Any questions about burnout?
For a lot of the people here, could you explain how they should have recognized it to be a hard problem as opposed to an easy one?
I recognized that as a hard problem as soon as I read it. I said, oh, good heavens, I don't know what particular thing about the problem I can tell you to see to catch that. I would say, you just need to go through practices. One thing immediately that comes to mind is parsing. Parsing is always challenging. Even the most simple things, parsing is challenging in a contest. So, parsing would have immediately, to me, pushed it to the back burner. It would have been one of the last problems I tackled simply because of the parsing. After that, once you start working with it a little bit, I believe the strategy that I always taught, I don't know, I think the Proj is that you read through the problems, but you don't sign up for a problem until you have a good understanding of what the solution is. So, you can read through this problem and see, well, I'm going to have to keep track of that. I'm going to have to, the number's too big. I'm not going to be able to simulate it. So as these thoughts go through your mind, you should be developing a picture that says, this has a lot of corners and edges, and I'm not ready to sign up for this yet until the end of the contest.
So for the issues with parsing that people had, would it have been sufficient to just take in the string and then basically tag everything with spaces to make it more easily tokenizable?
In fact, some of our judges suggested we do that with the judge data, but we wanted this to be a hard problem, so we didn't. But as long as you don't separate the digits of an atomic integer, as long as you don't separate the 1 and the 9 of a 19, whatever floats your boat, whatever makes it easier for you. If you can then do dot split with \s plus to split on spaces, that's cool. That'll work.
I mean, something I'd recommend is actually just go character by character and do special cases for parentheses and the star character, and if it's a number, check if the next character is a number. If not, then treat that as a number, or keep building the number as necessary.
My code will be out there, so you can see how I parsed it, if that helps.
Was the runtime pretty easy, or do you remember the expected runtime?
This was, I don't release the exact numbers, but this had among the shortest. If you do it the right way, if you do it the wrong way, it'll take millions of years. But if you do it the right way, it can be done in by 1 or 2 seconds. Anything else? All right, what's next? Family fortune?
Yeah.
This is a fun one. All right, my programming by the numbers friends. What is the limit of n? There are two numbers, n and k. What's the limit on n?
100,000.
100,000. What's the limit on k?
1,000.
About 100 million. So we intentionally chose the numbers on this problem to force you into an order n times k solution. This was intended. We thought that this was the hardest problem in the set, mainly because, well, the code itself is fairly easy. And I know that 2 teams have, after the contest, written solutions. Yours has.
Yeah.
UCF did also. There is a solution, but a lot of standard solutions, you may know, won't fit because they're order nk squared or n squared k or things like that. You have to apply a little bit of cleverness and think outside the box a little bit to come up with the algorithm for this problem. So the problem is, I should talk about the problem. You're given a tree and every node in the tree has a number on it, which represents the wealth of a family member, you have to, and you're given a tree with n nodes, up to 100,000 nodes, and k is the size of a subset. You have to find a subset of size k with the maximum sum, with the caveat that no node in the subset can be a descendant or an ancestor of any other node in the subset. Okay? Remember that? So, let me just go straight to the solution. We're doing okay time-wise. Let's go to... Yeah. Let's see this. Pardon? Okay. This is going to be a dynamic programming problem where we do a post-order traversal of the tree. So whenever we're at a node, we're going to go through all of its children and see what the best sums we can get from all of its children, and then we're going to look at its values, and see if we do better using its children, or if we do better shunting off its children and using it. Make sense? That's about it. So, we're going to pass in what node we're looking at, and the sums that we've computed so far, and sum sub I is the best we can do, adding up I nodes with all of the nodes that we've seen so far. Make sense? So that's what sums is. So we make a copy of that to pass down to the children, and then we pass it down to all the children, to this one, see what it can do, then pass it on to all the children. So we get an array, which is the best that we can do if we ignore this node and only use its children. Then we have to see what's the best we can do if we use this node, and that's what this if is all about. So we start at k and work our way down, and forget that, I need to clean that up. But, as I say, this needs to be cleaned up before I post it on my blog. That's what this weekend is going to be all about. It's going to be... Okay. So, sums is what was passed in. So, we look at I minus 1. That's how far we got up to I minus 1. If that's greater than 0, 0 is a flag that we haven't gotten there yet. So, you know, if we've only seen 3 nodes, sums of 5 will be 0 because we haven't seen 5 nodes yet. Okay? 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 Okay. All right. Okay. So, sums of I is equal to, well, let's see, if we've gotten this far, and if we add in the weight of this node to what we got with I minus 1 nodes, if that's bigger than what we could have gotten using the children at I, then we're going to use what we had before plus this weight and shunt off the children. Otherwise, we're going to use what we got from the children and ignore this node. Make sense? And the only other tricky part of this is down here, if this is number 1, if this is the first node, if it's bigger than anything we could have gotten from the children, we'll use what we got at this node, otherwise we'll use what we got from the children. 1 is this kind of a special case. The first one is 1 node. Make sense? That's it. And, you know, the code is actually fairly simple. And when you think through it, it's kind of simple. But coming up with that in contest time is a challenge. This was the problem that we had to modify for Java. We originally did not have the specification of a limit of a depth of 1,000. and we ran into Java not being able to recurse that deep. If you have 100,000 things in basically a linear list, Java can't recurse that deep. So we had to actually modify this problem to specify a limit of a depth of 1,000 so that we didn't disadvantage our Java code. More insight into how the judges think. Any questions?
Why is n times k instead of n times k0 compensated?
You will visit every node exactly once.
Yeah.
Every time you visit the node, you will do order k operations.
But every node you have to make an array of k, right? That's k to store. If you put k nodes in that subtree, if you select k nodes in that subtree, what is the max value you can get?
I'm sorry, I'm not following you.
Yeah, I mean, for every node you need a one-dimensional array to store its state. It's like
That's actually not, you don't need it for every node, you don't need it for every unit of depth. Well, this program, I'm using this one to show you because it's easier to understand. I've got another version which is a little bit faster, which pre-allocates the arrays. And you don't need an array for every node. You just need an array for every unit of depth. And if you go up and down in the recursion, just however deep you are, that's the array you use. Yeah.
So that's why you need that the depth is more than 1.
Well, that and because Java can't recurse 100,000 deep. Java can't recurse that deep. So, and we might have run into space problems if we recursed 100,000 deep and had 100,000 of these arrays. Might have been a problem. But it's order nk. It's not order nk squared. It's order nk because you visit every node exactly once. It's a post-order traversal. And at every node, you do order k operations. There are several of them. But creating a copy of the array is an order k operation. And this is an order k operation. So you do an order k operation at every node, and their n nodes, order nk. This code runs in about 7 to 9 seconds on a relatively normal machine with the judge data. Any other questions? All right, next on the agenda is moving points. Moving points. You've got a bunch of points that are moving, and they're moving at a constant speed in a constant straight line direction. Then you've got a chaser point, and the chaser point has to catch the moving point. This is essentially a traveling salesman problem. You know, what is the cheapest that you could visit? You don't have to go back to the original node, but yeah, who cares? You have to find the cheapest way to visit all of the nodes. Now, programming by the numbers. What was n here? What's the max n?
What is n?
15.
15. So, what kind of algorithm can you not use?
Factorial.
Factorial. We made this one of the harder problems. We wanted to be sure that you didn't simply use an n factorial all possible orderings. There is a standard algorithm for traveling salesman, which is order n squared to the n squared. We wanted you to use that algorithm. And in fact, you had to use that algorithm. If you tried to n factorial it, you would run out of time. So if you know that algorithm has to do with memoizing, you create an integer where each bit represents whether or not you have visited a particular node. You can call that a state. And so if you go to like node 135, then you go to nodes 153, then from 351, you visited the same 3 nodes. The nodes you have left to visit are all the same. So whatever you find that's best for those, you can just reuse them for each one of those cases. So that's kind of how the 2 to the n squared solution works. We wanted you to do that, plus it's got the extra little spice of some geometry to figure out the shortest distance where you could go and catch. And there's another little trick that I need to talk to you about in a minute. Any questions? I'm not going to go through the Towers, the traveling salesman algorithm. There are plenty of references for that on the web. But I am going to talk a little bit about the math. Anyone interested in the math? Math is fun. Uses my favorite thing in math. It's the law of cosines. You have no idea how useful the law of cosines is. So this is moving points faster. There we go. Check out this triangle. So, let P be the current position of the chaser point. Let Q be the current position of a target point. Okay? Let's say that target point is moving in this direction. We know the direction it's moving in. We know the speed. We know the speed of the chaser point. Okay? So let's form this triangle. Distance from P to Q. We know that. We know the point P. We know the point Q. We can just use the distance formula. So we can get D pretty easily, right? The distance from Q to R, which is the point of intersection, we don't know. But we do know it in terms of a time parameter, delta t. It's delta t times the velocity of that point. That, wherever it is, we don't know where it is. But wherever it is, it's going to be delta t, whatever this intersection time is, times the velocity of that point. We also don't know the length of this side, but we do know in terms of delta t. Delta t times the velocity of the chaser point. Does all that make sense? Okay. What are we missing to use law of cosines? Yes, we need an angle. Well, we can figure out the angle from P to Q using A tan 2. Beautiful function, A tan 2, by the way. If you don't know it, you should. A tan 2 is a beautiful function. So we can use A tan 2 to get the angle from Q to P. We know the angle of this. It's given to us in the input. So using those two, we can figure out the angle at that point in the triangle. So we've got 3 sides and an angle. We can come up with an equation for t, delta t and solve it. And it turns out that that equation is a quadratic. So we can just use the quadratic formula. We can take a look at a little of it if you like. Back up to the top for no good reason. So here's where the target point is now. Take the target and project it to this time. Take the target and project it to this time. Okay, first find the angle at Q. Lovely A tan 2. Beautiful function. By the way, YX is the location of the chaser point right now. So there. Angle minus equals theta, and then normalize the angle. Do some funny angle stuff. There's the difference. Another fun function, hypot. Fun Java function. That's the distance between P and Q. A, B, and C are the quadratic formula, and then just solve the quadratic formula. And being a judge, I put in a lot of stuff here. A panic, you've seen my panics before, just in case the numbers come out really bizarre somehow. This should be impossible, but in case it happens, let me know that something's really wrong with my data. Get the smaller delta time. If it's negative, you try the bigger one. If that's negative, then we've got another panic, but that never happened. So, there is one other conceptual hurdle we have to get over on this problem, which is we have made an assumption that moving at the maximum speed to intersect a point is the best thing we can do. So, let's say that our chaser point is here. Our target point is here, and is moving something like this. We've assumed that the best thing we can do is move as fast as possible to intersect the target point. Is that true? Is it ever better for us to move slower or to stop and to intersect it at a closer point? Can you prove that?
Yeah.
Cool. I can too, so I'm glad. What would your proof be?
Simply that because that thing moves faster, once you intersect it there, you can actually just move it back out there.
That's exactly the right proof. He gets a slice of pizza too. Yeah, give it to me. There you go. That's exactly right. The chaser point moves faster than any other point. So if you were to intersect it here, you can get to this point faster than the target point can. So waiting for it makes no sense. So you could get there and then go somewhere else and have this zigzag, or you could go directly there. Going directly there has to be faster than the zigzag. The zigzag has to be faster than coming over here and waiting. So there. Okay. Any questions about moving points? Okay. The last problem in the set was vampire numbers. This was intended just to give you a little more insight into how we do things. We characterize problems. We give it a difficulty letter. A and B are the easiest problems in the set. In this set, difference was an A problem. Well, this one, vampire numbers, was what we considered a B problem. Intermediate problems like Hexagram and Sunday Drive and robot navigation, those were all CDs. Folding game, moving points, and family fortune were all EFs. They were all problems that we considered hard enough for World Fun. So this was a B problem. There are tricky things you can do, but you don't need to. We kept the limit of x as 1,000,000, so all you have to do is start at x, add 1, add 1, add 1, until you find a vampire number. There is one little trick which is very useful that I'm sure that 99% of you know, but for the 1% of you, if you're trying to match anagrams, then you could compute what I call a signature, which is to take the letters of the thing you're anagramming and just sort them. So if you have a bunch of different words, if you take the letters and sort them, if they match, then obviously they have the same. And so you don't have to do a lot of searching. You can just sort the letters and then compare that signature to see if two things anagram to be the same thing. And so that's kind of the way the vampire numbers solution works. Go there. So this is simply the code. Reading x if it's 0 break. Otherwise, while it's not a vampire number, increment it. Print it. Easy enough. Vampire itself is vampire. Compute the signature of x. Then find all of its factors. This is a cute little trick. I equals to I times I is less than or equal to x. Cute little trick. If x is divisible by I, then get the signature of concatenate I with x divided by I. If the signature is the same, then it's a vampire number. And the signature is simply create a character array, sort it, return the string. Any questions at all about vampire numbers?
With that for other program, they didn't mention number of test cases, and I assume that there are a few number of test cases.
You cannot. I know that I've heard from Tapraj that particularly here in Georgia Tech there has been great gnashing of teeth about input sizes and timing of programs. What can I do to stem the tide of that? What can I do to keep you guys from worrying about that? What the judges do is run their programs on the data. They then take the slowest of the judge programs, and they run it on all the data. They don't run it on a single case. They run it on all of the data. And so any timing we come up with takes into account all of the data, however long or short it is. You don't have to worry about whether there's a lot or a little. The judges have taken that into account. But they take the slowest problem. If it's slow enough, we multiply it by 10. If it's not slow enough, then we come up with some other multiplier. We will never give less than 10 seconds. 10 seconds is the minimum that we will give. But it's based on how fast the judges. Except there was one case, a guy wrote some solutions in Haskell this year, and the Haskell solutions took like 6 minutes on some of them. We can't take 60 minutes for Judge Tom. We can't do that. But but for the solutions that ran in relatively normal periods, and some of the Haskell solutions ran faster than some of the Java solutions on some of the programs. For things that ran in normal times, we took all of the judges, take the slowest of the judges, multiply that by some multiplier. I see you. I'll get to you in a second. Multiply that by some multiplier, and that's the time we give the students. You've heard Kapraj and me talking about programming by the numbers. We are very aware of that at Southeast Regionals. We choose the numbers very specifically. We choose the timing very specifically to indicate what algorithms we are expecting to be used to solve the problem. It has never been the case that if we gave a problem an extra second or two, it would have been judged correct. Never has that happened. It has either been well within our bounds or well outside our bounds. The discriminator is the algorithm used and or infinite loop, not little tweaks and fiddles.
Yeah, but for this program, you can pre-compute all the answers or inputs, right?
The number could be anything up to, what, 1 million?
It's like it's like 100,000.
1 million.
1 million. You can do 1 million.
If you can pre-compute all the vampire numbers, actually my program runs in like 20 seconds. And in the contest, I'm worried about it didn't work because it kind of.
No. Yeah, well, it depends on the language, but no. It would not have run out of. We gave this one a lot of time because there was a lot of grinding that went on, and plus it was a problem that we considered a B. We wanted a lot of people to get it, so we gave a little bit of extra. We gave a time threshold to make sure it would work. Although I will tell you this: if you hard code all your answers and they're correct, you get it right. We don't look at the code. If you hard code all the answers and if they're correct, you get it right. Say that again? Well, I mean, if there are millions of them, yeah, it could be. But
in the context of figuring out whether or not this solution would run in time, without, I guess...
You guys are just so obsessed with that.
No, just making an argument as to why someone might think that. It's just that if you look at this problem and don't know how dense these vampire numbers are, then theoretically it could be x squared, 1,000,000 times 1,000,000, because you might start at a very low number and just start going upwards, and then you just won't find one until you find the farthest reaches of 1,000,000.
Do some experimentation. Write a program. Yeah. Okay, n can be anywhere from 10 to 1,000,000. What 2 data cases should be in your test input? Louder. The first one is, the second one is, try it. See what it does. One thing on flooring tiles that floored me, that frustrated me. I had a team getting the problem right except for one case. Every number was right except for one case. This one.
Did they finally get it right, or?
I don't know. Wow. I'd have to go back and check because at the end of the contest, it's a flurry. Yeah. I couldn't. I wanted so badly to send them a message.
Yeah.
The correct answer is 1. They were answering 2. Everything else, the bigger cases, 1 through 2 through 75, every other number was right except that one.
I see that FIU submitted it 6 times, so maybe
Maybe it was FIU.
and they got it right. So
Did he get it right? Oh,
Yeah,
that's good.
at
That's
280.
good to know. I'll go back and check.
It'd be funny if that team solved 7. If they solved 7, because 8 would have beat our team here.
Well, I'll tell you, UCF told me afterwards that they had come up with an algorithm for Family Fortune, but they didn't code it because they thought it would take too long. But that night, they coded it, and it took 7 seconds on their computer. They would have gotten it. They would have gotten it if they had coded it in time. But they didn't, and that's the point. So, you've got the chief judge in front of you. What else do you want to know? Any questions from the web audience? Do we have a way for them to ask questions?
They could leave comments on the.
they could chat, but
Nobody's doing it? What are they saying? I wish that guy would
one of the
shut up.
guys says, anti-port bomb says, I suffered from burnout. That was a long time ago.
Yes. Quite a few people suffered from burnout, and the judges did too. The judges did not want to see that happen. Any questions? Well, thank you all for joining me. Is there anything else I want to talk about? No, it really takes me too long to talk about our process, so I don't want to talk about that.
Maybe next week or some other time in spring semester.
Yeah. Invite me over anytime.
Oh, UF says hi.
Hi, UF. Is that David Small?
I don't know. He's named anti-port bomb, so could be anybody.
Heaven knows. Heaven knows who it is. Well, say if it's not David Small, say hi to David Small for me.
You can say hi now.
You are saying hi.
Hi.
Oh, he's a student. Yeah.
Anything else? Anything else you want to know? While you got me. Okay.
Well, I hope we can make this a weekly, a yearly event. After, not a weekly event. After each Southeast regions, hope we can do this kind of thing so that all the students are burning to know the solutions can know it. So let's thank Van B, guys.
For those of you who were not at FIT, I get to announce this at FIT, but the people who are not at FIT don't get to hear this. You go to serjudging.vanby.org, and at the instant the contest is over, the judge date is up. Judge date is there. You can grab it and have fun with it. All right.
Cool.